Hi, let's take some more previous year gate problems from the chapter bending of beams. Okay, so in this problem, a cantilever beam having square cross section of side A is subjected to an end load. Okay, if A is increased by 19%, the tip deflection decreases approximately by. Okay, it's a very simple question consisting of basic mathematics. So a beam is subjected to an end load, and we know that when suppose it is subjected to an end load P, and when the cantilever beam is subjected to end load P, the deflection is given by PL cube by 3EI. This is the standard result that we remember. L is the length of this cantilever beam and EI is the flexural rigidity. Okay, so for square cross section, I is equal to moment of inertia is equal to A raised to the power 4 upon 12, because it is a square cross section. So this is the moment of inertia. Okay, so when you put this value in this formula, you see that deflection is inversely proportional to A raised to the power 4 only. Okay, and if A is increased by 19%, so that implies new deflection will is inversely proportional to 1.19 A raised to the power 4. Replace it with a constant sign. It's a same thing. That implies K. Let K be a constant because all other terms are constant. So this is deflection new. Okay, now I have to find the tip deflection decreases approximately by. Okay, so percentage decrease in tip deflection, that is del new minus del, let it be del old upon del old into 100. This is n. Okay, so this is given by 1 upon 1.19 raised to the power 4 minus 1 into 100, which is equal to 50.133%. Okay, so the tip deflection decreases approximately by 50%. Option D is the answer. Okay, next problem. So in this problem, there's a figure which is given to us, and the figure shows cross section of a beam subjected to bending. Okay, the area moment of inertia of this cross section is, so you have to find the area moment of inertia. Very simple question of this cross section about its base. Okay, the keywords, you have to find the area moment of inertia about its base, not about its centroidal axis. Okay, this is the centroidal axis, because the semicircles that have been cut from this rectangle are symmetrical, and this is the centroidal axis. Okay, so what I can do is I can find the moment of inertia of this rectangle about its centroidal axis. I can find the moment of inertia of these two semicircles or a circle about its centroidal axis. I can subtract both of them, and then I can apply parallel axis theorem and find the moment of inertia about this cross section about its base. Okay, so moment of inertia of this circle. Okay, two semicircles make a circle, we know. So I circle is equal to pi by 64 d raised to power 4. D diameter of the circle is 8 mm. So when we solve this, we get moment of inertia of this circle about the centroidal axis is 201.06 mm raised to the power 4, and moment of inertia of rectangle is given by bh cube by 12. This is b, this is h, because this centroidal axis xx is parallel to b, so it will be given by b, and the other side will be h, which will be bh cube by 12, the moment of inertia of rectangle. This is 10 into 20 cube by 12. Solve it. This will be is equal to 6.67 mm raised to the power 4. Okay, So the total moment of inertia of this cross section about the centroidal axis is moment of inertia of rectangle minus moment of inertia of this circle. So this will be minus 201.06 mm raised to the power 4, which gives us the value 6465.61 mm raised to the power 4. Okay, this is the moment of inertia of this figure about its centroidal axis, but we have to find the moment of inertia of this cross section about its base. Okay, so now applying the parallel axis theorem, which states that I is equal to ICG plus AH square. Okay, so ICG, we know ICG, that is 6465.61. Area we can find out, which will be equal to the area of this rectangle, that is 20 into 10, minus the area of this circle, which is pi by 4 8 square, pi by 40 square. Okay, and h is the distance between the centroidal axis and the axis where you have to find the moment of inertia. So this is 10. Okay, this is 20 actually, this is given incorrectly. Okay, this h is 20. Okay, so this is 10, h is 10. So solve it, put the values, and you'll get the answer. So I is equal to ICG, that is 6465.6 plus 20 into 10 200 minus pi by 4 d square into 10 square. So this will be 21439.058 mm raised to the power 4. 21439.058 mm raised to the power 4. This is I of this cross section about its base. Okay. Let's move on to the next question. A simply supported beam of length L is shown with the given loading. It is given that P is equal to 1 Newton, L is 1 meter, and Young's modulus is 200 GPa. The cross section is square and the dimension is 10 cross 10. The bending stress at point A, the bending stress in Pascal at point A located at the top surface of the beam at a distance 1.5 L from the left end is. Okay, the sign convention has also been given. So for finding the bending stress at point A, what I have to find first, I have to find the moment at point A. That is how I can find bending stress, by bending equation, because m by I is equal to sigma b by y. Okay, if I find the moment at cross section passing through A, I will be able to find the bending stress at this cross section. Okay, so there will be a reaction. Let this be point C, this be point B. Let there be a reaction RB and RC here, and sum of moments around point C is equal to 0. We can write this. So PL minus 2PL. Okay, this is P into L, taking the anti-clockwise sign as positive, taking the proper sign convention, minus 2PL, and this is again minus RB into 3L is equal to 0. This part is easy, you can solve. You can find RB, which is equal to minus P by 3. Okay, so actually the direction is opposite, that is RB is acting in downward direction. This is the actual direction, so this is P by 3. Okay, let me rub this. So RB is P by 3 in the downward direction. This is RB. Okay, now moment at cross section passing through A, let it be denoted by MA. So P into L by 2, okay, plus minus p by 3 into the distance, that is 1.5 L, okay, which is 3 by 2 L is equal to 0. So when you solve this, oh, this becomes 0. So there is no moment at the cross section passing through A. That implies sigma B will be 0. Okay, so 0 is your answer. Okay, next question. The next question is, a rigid horizontal rod of length 2L is fixed to a circular cylinder of radius r, as shown in the figure. Okay, vertical forces of magnitude P are applied at the two ends as shown. The shear modulus for the cylinder is G and Young's modulus is E. The vertical deflection at point A is, okay, so I have to actually find the vertical deflection at point A. Okay, so suppose this is the rod. Okay, this is actually the circular cylinder on which it is attached. There's a load P acting down in downward direction. There's a load P acting in upward direction, and they will actually try to rotate the rod in clockwise direction, and due to these two loads there will be couple that is actually rotating the rod in clockwise direction. So this point A will try to move upwards. Okay, it will try to move upwards, this point A. So let that it moves by a distance y upwards, making an angle theta here. Okay, so if it moves y upwards, this point, suppose it is B, it will move y downward, again with the same angle theta. Okay, so I have to find this I have to find the value of this y. Okay, so can I say that tan theta is equal to y by this distance? What is this distance? The length of the rod is given as 2L. Okay, so this is L and this is also L. Okay, so tan theta, this tan theta is equal to y by L, and as theta is very small, can I write tan theta as approximately equal to theta? Okay, so theta is equal to y by L, and y is equal to theta L. So if I find theta L, I know I will be able to find y. Okay, how can I find theta? Okay, you know that these two forces are actually forming a couple, are actually forming, actually rotating the rod. They are exerting torque on this rod. So can I use that torsion equation, which is T by J is equal to tau by R is equal to G theta by L. Okay, so I can equate these two equations and find theta. So T by J is equal to G theta by L. That implies theta is equals to TL by GJ. Okay, now let me ask you, what is the total torque? It will be 2PL, not PL. Okay, because this load is exerting a torque PL in clockwise direction, and this load is also exerting a torque PL in again the same direction, clockwise direction. So total torque will be 2PL. Okay, so this is 2PL into L upon G into J. J is pi r raised to power 4 by 2. Okay, so this becomes this is, when you solve it, it will be 4 PL square by pi G r raised to power 4. Okay, so this is theta, and now y is equal to theta L. So multiply it by L and you will get the vertical deflection of point A. Okay, I guess the options are missing in this question. Let me see. The options are not given in this question. Okay, so our answer will be 4pl cube pi g r raised to the power 4. So 4pl cube pi g r raised to the power 4. This will be our answer. Okay. So this was actually a nice question. Next problem is the cross sections of two solid bars made of the same material are shown in the figure. The square cross section has flexural rigidity I1 while the circular cross section has flexural rigidity I2. Okay, so flexural rigidity is EI. For the first cross section, that is a square cross section, its value is I1, and for the circular cross section its value is I2. Both have the same cross sectional area. Okay, so A1 is equal to A2. I have to find the ratio of I1 and I2. Okay, I will directly cancel out E because both the cross sections are made of the same material. Okay, so this is I1 by I2. I have to find. Okay, what is I1? I mean the the moment of inertia for a square cross section is a raised to the power 4 by 12. Let the side of this square is a. Okay, and the diameter of this circular cross section is d. Okay, so I1 is a raised to the power 4 by 12 and I2 is, you know, that pi by 64 d raised to the power 4. One more condition is given, that is A1 is equal to A2. Okay, so area of square is a square and area of circle is pi by 4 d square. I can find the relation between a and d from here. That implies a by d whole square is equal to pi by 4. Okay, so this becomes a raised to power 4 I1 by I2 is equal to a raised to power 4 by 12 divided by pi by 64 d raised to power 4. Okay, so put this relation in this equation and you will get your answer, that is a raised to power 4 by 12 into 64 divided by pi d raised to power 4. So this is a by d whole square is equal to pi by 4. So a by d raised to power 4 will be pi by 4 whole square into 64 by pi into 12. Okay, so when you solve this, this will be pi by 3. So the option is C. C will be the answer. Okay, let's move on to the next question. A beam of length L is carrying a uniformly distributed load W per unit length. The flexural rigidity of the beam is EI. The reaction at the simple support at the right end is. Okay, so let this point be A, let this point be B. Okay, so when this load, this uniformly distributed load is acting, there will be a reaction at B in the upward direction. Okay, this is a case of propped cantilever beam. Okay, and due to this reaction RB, deflection at B is 0. We know this. But if there was no support at point B, the deflection would have been WL raised to the power 4 upon 8 EI. This is a standard result that we remember when a cantilever beam is subjected to a uniformly distributed load of W per unit length. Okay, so if there was no support at B, there would have been no reaction at B, and hence the deflection at point B would have been WL raised to the power 4 by 8 EI. But as there is a reaction at B, so this reaction is actually stopping this deflection. Okay, and we also know that when a cantilever beam is loaded at the free end by a point load P, its deflection is PL cube by 3 EI. Okay, so can I say that this reaction is actually exerting a deflection PL cube by 3 EI in the upward direction. Okay, so due to this uniformly distributed load W, there is a deflection in the downward direction whose value is equal to WL raised to the power 4 by ATI, whereas due to this reaction there will be a deflection in the upward direction and whose value will be equal to PL cube by 3EI. So I can equate both these deflections and I will get my reaction at B. This is RB L cube by 3EI. Okay, so solve it. RB will be 3WL by 8. Okay, so this was an important concept. Okay, so the next question is, a simply supported beam with 100 mm, this is mm, height 200 mm and length 4 meter. Okay, height is 0.2 meters, width is 0.1 meters and length is 4 meter, is carrying a uniformly distributed load of intensity 10 kilonewton per meter. The maximum bending stress in megapascal in the beam is. Okay, so the maximum bending stress will occur at the cross section where there will be maximum bending moment. Okay, by bending equation, M by I is equal to sigma B by Y. Okay, so if this is maximum, this will be maximum, and the maximum bending moment in case of a uniformly distributed load occurs at the center cross section of the beam and its value is equal to WL square by 8. Okay, we do remember this value. You can also find out by making a simple bending moment diagram. Okay, so this will be maximum bending moment. Okay, so M maximum is WL square by 8 and W is 10 kilonewton per meter, that is 10 into 10 to the power 3 Newton. L square is the length of the beam, that is 4 meters upon 8. So this comes out to be 2 into 10 to the power 4 Newton meter. Okay, I is the cross section is, width is 0.1 meters and height is 0.2 meters and it is bending around this x-axis. Okay, so this will be BH cube by 12. B is width, H is height. Okay, so BH cube by 12 and y will be equal to H by 2. So y is equal to H by 2, that is 0.2 by 2, 0.1. Now I can find out sigma B maximum. This will be sigma B maximum if this is maximum. Okay, so let's solve this. This will be 2 into 10 to the power 4 Newton meter into y is 0.1 upon I is 0.1 to 0.2 cube 12, which is sigma B maximum. Solve it. This will be equal to 30 megapascal. I'm directly writing it in megapascal. You will get the value into 10 to the power 6, but as I have to find the answer in megapascal, I'm writing the answer directly in megapascal. So this is 30 megapascal. Okay, be careful that in which units you have to fill the answer. Okay, thank you.